What's up, everybody? Today we are talking about chemical kinetics. Chemical kinetics study the speeds of reactions, right? So in chemistry, we study reactions, the changes that matter goes through. However, some reactions happen in a split of a second, and some other reactions happen for millions of years. It's crazy. So we are going to talk about the speeds of reactions and how we calculate them and how we categorize them and things like that. Now, this is going to involve a bit of calculation and a few formulas. So make sure that you take notes and step by step solutions so that you know how to solve some of the problems regarding kinetics. I will warn you that this is one of the chapters that students find difficult, but that is number one, if they disregard remembering the formulas, and then number two, if they don't follow the step-by-step reactions, and more importantly, if they don't understand the full picture of what we're trying to do or what the reactions mean. So make sure that you pay a little bit more attention to this one. But let's get started. All right, so chemical kinetics, as I was saying, studies how fast does a reaction go. So the speed of reaction. Now we'll talk a little about thermodynamics, and thermodynamics has to do with the energy of reactions and whether or not that reaction is actually going to take place. So we have kinetics, thermodynamics. I don't know if it's the next chapter, but we will talk about that too. Why? Because chemistry is the study of matter, the changes that the matter goes through, that's the reactions and kinetics, and then the energies that are involved in those changes, that's thermodynamics. But we'll talk about that. And when it comes to kinetics, we are going to talk about a few things that I want you to know about. The number one is reaction rates. Reaction rates, right, is the reaction speeds, right? So we're going to talk about how we measure the reaction rates. We're going to talk about rate laws. We're going to talk about the integrated rate laws, right? We're going to talk about half-life. We're going to talk about something called Arrhenius equation, and then we're talking about a little bit of kinetics when it comes to mechanisms, right? So again, kinetics studies the rate at which chemical process occurs, right? And we will talk about the mechanisms as well. So let's start with rate. So the reaction rate is speed. So whenever you hear rate in kinetics, think of speed, right? So it's a change in the concentration. You see what just happened, right? When we talk about speed in running, or I don't know, when you're driving, you drive 80 miles per hour or less, hopefully, right? That is distance over time. Distance over time. But when we're talking about speed in chemistry, we are going to look at chemicals over time, concentration over time, right? So the reaction rate is going to be equal to the change in concentration, right? So let's say we have A going to B, right? It's going to be the change in A over change in time, right? And guess what? It's going to be either the change of the disappearance of A or the change of appearance of B, right? And if we want to illustrate it on a formula, this is what we're going to do, right? We're going to say, okay, rate is going to be equal to delta A. Delta is change, right? Delta A over delta T, change in A over change in T. But guess what? We're going to have to give it negative because it's the disappearance. It's the disappearance, right? I want everybody to understand that, right? So if we start with 10 molar, and then we end up with 2 molar, right? The change is going to be 2 minus 10, right? It's going to be negative. It's not that simple, but if it's negative 8, it's negative. That's why we put negative in front, right? But if we're measuring the rate with the appearance of the product, we are going to have a positive. Why? Because the product goes up, right? It will be going from 2 molar, oh no, 0 molar, right? Because we haven't made any product, right? It's going to be from 0 molar to 10 molar, for example, right? So the change in product goes up. That's why we don't have a negatives. A lot of people get confused about that, so I want to make that clear. And then let's talk about this. Let's see. Let me make sure that I save this first, because if it's not saved, then you won't have access to it. Come on. There you go. All right, we're back. So if I have a reaction, right, we're going to start with the reactants, right? So if A is going to B, we're going to start with A. And then over time, you start to make B, which is red here, right? And then over time, eventually you're going to end up with most of B. So again, the rate is the change in concentration of A over change in time, right? And on a typical reaction, you start with all of A and no B, and then it's going to go up, right? The B goes up and then A goes down, right? A is the reactants. The reactants are being used up to make the products, right? So why do we express the rate in both the reactant and the product? It's because depending on the reaction, it's very hard to measure the rate, right? For example, this one is a cool reaction. It's very dangerous, but it's cool, right? If you have bromine plus acetic acid, this is a typical reaction that's going to produce CO2, right? This reaction is going to change color, right? It's going to change color. So the disappearance of brown, bromine is brown, right? The disappearance of brown is what we're going to measure the change in the reaction. So we're going to measure either the disappearance of the product, of the reactant, or the appearance of the product, depending on the nature of our reaction, right? So that's why we have to make sure that we know whether we're measuring the product or the reactant, right? So we can measure both. If you are measuring, right, look at this. If you're measuring the disappearance of the reactant over time, right? This is the reaction we just looked at of bromine, right? You can measure what we call the absorbance to see the change in color, so that we can convert that into concentration. And look at that, the concentration of bromine 2 goes down, right? So how do we find the rate? The rate is going to be the slope of this. If you plot this on a graph, it's going to be the plot. But again, do not worry too much about this. We're going to just measure at some point. We're going to measure the change, right? We're going to take 2 points, and then we're going to measure the change in bromine over change in time, right? So bromine final over bromine initial over time final over minus time initial, right? So this is the rate. So if I give you a table and I ask you to measure the rate, that's how you're going to measure the rate, the change in concentration over change in time, right? So that's how we measure the rate. All right, so again, if you have, right, and this is kind of going to the next step, right? If you have, instead of having A goes to B, right? Instead of having A goes to B, now you have 2A goes to B, right? So stoichiometry is telling you that 2A is going to give you B. How do we factor it into account? When you're measuring the rate, guess what you're going to do? You're going to have this 2 be at the bottom here, right? 1/2 of disappearance of A over time is going to be equal to the appearance of B over time, right? So the overall reaction is shifted, but the overall reaction, or the overall equation, right? If want you to give me the rate, the overall equation is going to be, it's going to involve the coefficients, right? We have to keep in mind that not everything is a one-on-one ratio. It's not like one gives one. No. So 1 over a, right? So if you have a here, you say 1 over a times the change in a over time is equal to 1 over b times the change in b over time, and then is equal to 1 over c times the change in c over time. And as we usually do, and we now know why, the reactants have negatives because it's the disappearance, right? So this is how we illustrate the change. So I can ask you like, hey, what is the rate expression of this reaction, right? What is the rate expression of this reaction? What is the rate expression of this reaction? And notice that we have 1 here, 2 here, or 1 here, then 2 here, right? So the rate expression, that's the next one. So the rate of the reaction, now we know about the rate expression. So if I ask you what is the rate expression, it will be the negative delta CH4 over delta T. By the way, if you haven't noticed before, if you didn't know, if I have A as a chemical, the brackets around A mean the concentration of A. So this is change in concentration of CH4 over time, negative change, -1 over 2 because you have 2 here, change in concentration of O2 over time, and then same here is equal to change in CO2 over time, change in time, which is equal to half because we have 2 here. So the rate expression, so rate constant, let me actually write the things that we need to know down here so that I will come back to them. So we need to know the rate and what it is. Then we need to know the rate expression, right? All right, and then after that, we need to know the rate law, and that's what I'm going to talk about, right? Rate law. What's the rate law? Well, it is another way we express the rate. Why my circles have shifted, that's okay. All right, so if I have a typical reaction, right, like this, good. Okay, so if I have a typical reaction like this, A is equal to A times B, A times A plus B times B, not times, but this is a coefficient. You get what I'm saying? 2 reactants give you 2 products. Then we can express the rate. Instead of the rate expression, we can express it in terms of both concentration of the reactants, right? So rate is equal to K. Actually, I can just show it to you. So the rate is equal to K, which is the rate constant. We call this the rate constant, right? Times A to the X times B to the Y. Notice that this is X and Y. These are not coefficients, right? So we don't use X and Y are not necessarily A and B, right? So the rate law is equal to K, which is the constant, right? Every reaction has a constant times A times B, right? And then next to A and B, we have X and Y, and these are what we call the reaction orders. The reaction orders, right? So it's telling you that A is at the order of X, B is at the order of Y, and then the overall order is going to be equal to X plus Y, right? And I will show you in a minute what these mean, but the rate law is going to be how we express the reaction, right? So like K to the A, X, and B, Y, and X and Y are what? They are reaction orders. Reaction order, and then X plus Y is equal to overall order of the whole reaction, right? So X is the order with respect to A, B is the order with respect to no, Y is the order with respect to B, right? So I want everybody to understand, like I said, I don't want you to just be looking at these formulas. So I want you to understand, why do we have two reaction orders? It's because if I have a reaction, right? They say I have a reaction A plus B is equal to C plus D, right? The rate of the disappearing of A is not the same rate of the disappearing of B, right? So A might disappear really fast, B might disappear really slow. And the same thing, the rate of appearing of C is not the same as the rate of appearing of D, right? These are different chemicals. So because of that, we're going to have the order with respect to A, and then the order with respect to Y, and then when you add them up, you're going to get the overall order, right, of the reaction. Very important, very, very important distinction, right? So again, another part of this is called the rate constant. The rate constant varies at every reaction, right? So the rate constant also varies at different temperature. These are factors that affect the rate constant. Temperature, the concentration of the reactants, and then the catalyst. Catalysts are things that speed up the reaction, right? So these are things that affect the rate constant. All right, so let's talk about the reaction rates, actually, right? So how do we measure the reaction orders? And before we do that, actually, let me talk a little bit about how to find some orders, right? What are the orders and how can we find them? So the order, we'll talk about these and I will give you a summary, but we have zero order reactions, first order reaction, second order reaction, and so on and so forth, right? And what do I mean by the order? I want you to understand. So when I say the order, and when I say the different ways of appearance and disappearance, what I'm saying is this, right? If I have, how do I say this? Okay, so if I have A plus B, and I increase the amount of A, so I say A plus B is equal to C, and then I increase the amount of A twice, right? What happens to the reaction speed? Right? Let me ask you this, like, think about this. If I double the concentration of A, what happens to the reaction speed? What if I triple it? Well, this is a trick question because it depends on the order of the reaction. That's what we mean by the order of the reaction, right? Sometimes you might have A plus B, right? And this will help you very well, right? So if you have A plus B, all right, it's equal to C plus D. And then let's say we start with, I don't know, 2 molar of A and then 2 molar of B, right? And then the rate or the reaction is going to be, let's say it's a decent 1 molar per second. Actually very slow, right? That's the rate. So if I multiply A by 2, so this becomes 4 molar, B is still 2 molar, right? What happens to the rate? What do you think happens to the rate? And again, if you multiply by A, right, and the rate is still 1 molar per second, so the rate doesn't change, What does that mean? Guess what? It means that it is a zero order reaction, right? It's a zero order reaction because the rate doesn't change. So zero order with respect to A at least, right? Zero order reaction. But what if when you multiply this A by 2, then the rate also multiplies by 2. So the rate goes from 1 molar per second to 2 molar per second, right? So every time you multiply by 2, multiplies by 2. You multiply by 3, multiply by 3. It's a one-on-one relationship. Guess what type of order that is? That's right, the first order reaction, right? So first order. First order reaction is when you multiply it by the rate, the other one multiplies the same way. That's the first order. But guess what? What if you multiply twice, right? So when you multiply this, by 2, instead of this multiplying by 2, it multiplies by 2 twice, or it multiplies by 4. So instead of it being 2 molar, it's 4 molar, right? So it went from 1 molar to 4 molar when you multiply. So you multiply by A by 2, but then the rate multiplies by 4. You go, wait a minute, this is a lot. This is when you know you have a really fast reaction. It's a second order reaction, right? So you have zero order when you multiply, nothing happens. First order when you multiply, it multiplies the same way. Second order reaction when you multiplies, and then it multiplies twice, right? Second order reaction. Does that make sense? So I want you to know the difference between first order, second order, and third order reaction. But then how does it manifest when it comes to equations, right? Because believe it or not, we calculate these differently, right? So look at this. And I don't want you to be confused by this, okay? I want you to take your time. It might look daunting at first, but take your time. So we're looking at a typical reaction, A goes to B, right? Let's say a typical reaction, A goes to B. Remember, we say that in this reaction, what's the rate law for that reaction? If you remember, the rate law says rate is equal to K times the concentration of A to what? To the X, which is the order, right? So guess what? If your X is 0, if it's 0 order, the rate is going to be equal to K times A to the 0, which is 1. So the rate law will be like in a 0 order reaction, the rate law is the rate is equal to K. The rate is equal to K, right? What if you have the first order reaction? Then X here is 1. And what's the rate? The rate is equal to K times A to the first, so K times A, right? So this is where this rate comes from, right? And guess what? What if you have the second order? X is 2, so it's equal to rate is equal to K to the A square. All right. So that's the first part that I want you to understand. The rate law when it comes to 0, first order, second order. Now, how about the concentration time equation, right? Let's go back to the first order first, because I don't want you to be confused, right? So in the first order reaction, as we said, right, it goes down. This is what we call linear, right? The rate changes the same way. So look at this. In the first order reaction, right? In the first order reaction, A gives you B, or A gives you the product, right? A gives you product. So if A gives you product, right? As we already talked about, the rate is equal to K times A, right? And then we also talked about how the rate is equal to disappearance of A over time. right? So if we do a little bit of math, don't be intimidated, guys. This is not too much. But if we do that, we're going to equalize this because this is the rate, this is the rate, right? If we equalize this, we say equal negative of a over delta t is equal to Ka. And then how do we remove the fraction? We're going to add the natural logarithm here and then the natural logarithm here as well. And if we do that, we're going to end up with ln of a is equal to ln of a initial now minus kt. Does that make sense? I see some yeses and I see some no's. So let's do it. Let's actually do it, because in this slide in the book they just told you what it gives, but let's actually do it. So we know that rate is equal to Ka, which is equal to negative change in A over change in time. But guess what? Negative change in A is equal to negative change in A is the final concentration minus the initial concentration. So final concentration is A, initial concentration is A0, right? Over change in time, right? So here we have K times A is equal to negative A, because I took this negative, multiplied that by there, plus A initial, right, over change in time, right? Again, we're going to apply natural logarithm for these so that we can make it one line, make it linear instead of a fraction. So ln of Ka is equal to ln, right, of negative A plus A 0 over delta t, right? And if you know anything about ln, right, you know that this will be equal to ln of K plus ln of A, which is equal to ln of negative ln of A plus ln of A0, and this will be minus ln of delta t, right? So as you can see, you have ln of A here and ln of A here. So that when you move it around is what ends up giving you ln of A is equal to ln of A0 minus kt, right? Because delta t is going to be equal to the time minus 0. But either way, this is where we get the expression, and this expression is crucial. Why is it crucial? Is because now we just have a equation that has our final concentration, our initial concentration, and time. So it relates our final concentration, initial concentration, and time. All right. So another way we can do it is we can turn it into E, right? So these are the same equations pretty much, right? And again, I don't want to get into too much math, but these are the same equations, but we like the linear equation better. We like the linear equation better, the equation that gives us a straight line, all right? So as you can see, right, this is for the first order reaction. So going back to our table, right? If you do this for the first order reaction, you get this. If you do this for the zero order reaction, it's much easier because A is equal to A0 is equal to negative KT. And then if you do this for the second order reaction, you're gonna get this formula. So these are the formulas that link concentration to time. They link concentration to time. It's a very important distinction. All right. And let me see if I can get a nice, there's a nice table that makes it even clear. Let me see if I can find it. All right, this is it. I love this table because it puts everything together and it makes it easier. But again, some of the things we haven't talked about yet, but let's talk about the things that we've talked about, right? So for the zero order, we know that yes, the rate is equal to the disappearance of A, right, over change in time. But we've already seen that. We've already seen that it's like, hey, in a zero order, it's gonna be equal to K, right? Because it's A to the 0. In a first order, it's going to be equal to Ka, and then in the first order, it's going to be equal to Ka squared, right? And then when we take these two and then we make them equal, and then we do some math, we end up with something we call integrated rate law. The integrated rate law is going to show us these, or these are called linearized versions of the laws. Why do we care about this? I want you to look at this, right? So if you plot the concentration over time, right, of a zero order, you'll see the disappearance of the product. It will be linear, it will be a line. But if you plot the concentration over time over first order, it will not be linear, it will be going this way. Why? Because of this equation, right? And then if you plot the concentration over time of a second order, it will be even more steep, right? So if we are doing an experiment, which you probably will do in this lab, if you plot the concentration over time, you might be able to tell what order it is, because if you see that it's a line, then you'll know that it's zero order. But if you know that it's kind of a curve, you don't know if it's a first order or second order. However, if you plot, instead of, for example, for this one, if you plot ln of A over time, right, ln of concentration over time, this should give you a linear graph, right? Even though the concentration over time is a parabola, the ln of concentration over time should give you a straight line like this, right? And then here, if you plot 1 over A over time, it should also give you a straight line. So that's one of the ways that we can experimentally measure the rate order of the reaction, right? We can plot concentration over time, one ln of concentration over time, and 1 over concentration over time. And then depending on which one is linear, you'll be able to tell, like, oh, this is my order, right? So you can not only calculate the reaction order, but you can experimentally find the order. So let's see if I have an example, right? So example is the reaction 2A to B is the first order. So I already gave you, it's a first order in A, right, with the rate constant. So it gave you the rate constant, and then it gave you degrees Celsius, right? And then as you, how long will it take? How long will it take for A to decrease from 0.8 to 0.1 molar, right? This is a good question. I like this question because it's a straightforward question, guys. It's not, again, you got to be comfortable with math, but it's a straightforward question. So they gave us the biggest hint. It's a first order. For this equation, I mean, for this chapter, before you calculate any of these reactions, you gotta ask yourself, is this a first order reaction, second order reaction? And from there, you should be able to tell me, hey, what formula do I use? Because the formula will be different. But look, they gave us the rate constant. So they gave us K, right? They give us the temperature, which we probably won't need, but they also give us the initial concentration, so it's A0. They give us the final concentration, which is A, and then they're asking for time. All right, so again, you already have the formula for the first order that links initial concentration, final concentration, and time. So it's a matter of just plugging numbers in and then figuring it out, right? I would not solve it this way, guys. I would not solve it this way. I would just plug in the numbers first, right? It can be like, oh, okay, KT, K, you already have K, right? KT is equal to ln of A times ln of A. So I would add all of the numbers. So I would be like, okay, K, which is 2.8 times 10 to the negative 2 per second, right? Times T, which is our time, is equal to ln of A0. What's the ln of A0? Is ln of 0.88 over minus ln of A, which is ln of 0.14, right? You see how much easier this is? Because then, let me actually calculate this. We gotta make sure that we're actually doing this for real and practicing it, and you should calculate this too, right? So I'm going to say ln of 0.8. Make sure that you use ln, natural logarithm, not logarithm, right? 0.88 ln is equal to, and this also gives you a chance to practice on your calculator as well. So this is equal to negative 0.12, and then ln of 14 is of 0.14 is equal to negative 1.96, and then you have a negative here, so plus 1.96, right? So this one is going to be equal to, no, it's 0.16, 0.196, not 196. I don't know where I got the 196. This is why you had to practice, guys. So this is going to be equal to 0.076, right? So T is equal to 0.076. So T times this number is equal to 0.076, and guess what? T is equal to 0.076 over this number, which should give you 66 seconds, right? So this is how we solve problems if you have a concentration, initial concentration, final concentration, and then you have the reaction order, and then they give you time. However, they can give you, they can do it all the way around, right? And ask you for initial concentration, final concentration, right? Having given the time. If this reaction was a second order or a zero order, it will be a different question, right? So, for example, let's say that this was a zero order reaction. If it was a zero order reaction, if you remember, zero order reaction is that A is equal to A0. I guess it wouldn't be a zero order reaction because these are different, right? So in a zero order reaction, A is equal to A0. So you would do it differently. In a second order reaction, right? We go back to the second order reaction, right? You will use this. So you will plug your A here. You plug your A here. You will plug your A0 here. You will have plug your K here, and then you would search for T, which would actually be easier, right? But make sure that you know how to calculate things when you have a zero order reaction versus first order reaction, so on and so forth. That makes sense? bit down. All right, so now this is how we calculate the rate order. But how do we find it experimentally, right? How do we define it experimentally, not mechanism, not there yet. How do we measure the reaction order experimentally? So we do this by two methods, right? The first method is this. The first method is we do what we already discussed here, right? So we run the reaction, and after we run the reaction, we do three graphs. We do three graphs, right? So this is the graph method. We're going to do three graphs. It's going to be like this. We're going to do a graph of concentration versus time. Then we're going to do the graph of ln of concentration versus time. And then we're going to do the graph of 1 over concentration versus time to see how they look like. Okay? Now, if you do a graph of concentration versus time, and it's linear, meaning that it gives you a straight line, then you know it's a zero order reaction. If it's not a zero order reaction, it will not give you a straight line. If you do a graph of ln of A versus time, and you get a straight line, you know that you have a first order reaction. Why? Because of this equation from the first order reaction, right? And then if you do a graph of 1 over concentration versus time, and it's a straight line, you know that it's a second order reaction. So the first technique, measure the reaction orders, is the graphing method. The graphing methods where you graph your reaction over time and then see whether or not it gives you a straight line. I like that method. I've used it many times. However, it might not give you different specific orders. So that's why we use another method called a method of initial rates. Method of initial rates. So the initial rates method gives you, it's actually on this table. I love this table, man. So check this out, right? You can see it. Okay, so look at these rates. Different. So remember I told you that when you have a zero order reaction, when you increase the concentration, the rate does not increase, right? So you can measure different concentration, right? So you can measure concentration at different rates, right? That's why we call it initial rates method. You can measure different concentration. You can measure the rate at different concentrations, right? So the concentration of A is 1, 2, and 3 here. Same 1, 2, and 3. And if you have a zero order reaction, there won't be an increase. If you have a first order reaction, it will increase the same way, right? And then if you have the second order reaction, it will increase exponentially. By the way, it will increase by squares, right? If you can see, right, instead of this one being multiplied by 2, it will be multiplied by 2 square, right? This one, instead of being multiplied by 3, it's being multiplied by 3 squared. So that's the second order, is the square part, right? So this is zero order, first order, and then second order, right? So two methods and two methods to measure reaction order, right? Number one, you can graph it and see how it looks like. And then number two, you can vary the substrate concentration. And once you vary it, you can measure what happens to the rate. And if it stays the same, 0. If it multiplies the same way, first it multiplies by 2, it is a second order, right? So I like that. Let me see if I can have an example for you guys. This one, not. Oh yeah. Check this out, right? So if I have this reaction, right? I have this reaction between F2 and ClO2, right? And then this is the data. This is the data, right? Think about it. So the data is 1, 2, 3 of F, and then this is the concentration of ClO. And then I asked you, like, first of all, what is the order of reaction with respect to F2? Then you're like, okay, 1 to 2. We doubled F2 here. When we doubled F2, what happens to the rate, the initial rate? The initial rate, 1.2. So we have 1.2 here. 1.2 became 4.8. When we doubled 1.2, right? Instead of saying, okay, 1 to 2 is no, this is the number. This is the number of the reaction. Never mind. This is the number of the reaction, the experiment. I almost got it wrong. So 0.1 is the concentration. So 0.1 is the concentration, 0.1 is the concentration, 0.2 is the concentration. Here you have 0.01, 0.04, 0.01, right? So first experiment, we F2 stays the same, but this one multiplied by 4. So ClO4 is 0.1 to 0.4. So you multiply this by 4, and then you look at the rate. What happens to the rate? The rate also multiplied by 4. So that means that with regard to ClO4, you have the first order reaction. Why? Because it multiplied the same way, right? If you multiply by like 2, 5, so if you multiply this by 4 and then the other one multiply by 16, because 4 squared is 16, then it would have been a second order, right? But then here, so let's compare 1 to 2 then. 1 to 2, 1 to 3. We multiply 0.1 to 0.2, so we multiply F2 by 2. Then let's see what happened to the rate. The rate was 1.2 and then became 2.4. So we multiplied by 2, and this also multiplied by 2. So the reaction order with regards to F is also 1. So again, 1 is because when you double one, the other one doubles. And then when you double the other one, when you quadruple the other one quadruples. So this is how we design our experiment, guys. And I want you to realize something, right? These experiments have to be separate. You cannot double both of them. If you double both of them, you will not be able to search it, right? So one has to stay the same. That's why this one is the same. Why we quadruple this, and then if we double this one stays the same, right? So this is the initial rates method. This experiment has been done many a time, and then after that, guess what? You can write down the rate low, right? Like if I ask you, like, write down the rate low, you say rate is equal to K times our first, right, reaction F2 to the X, which is 1 now, right, to the other one ClO2, and then which is 1 Y, right? So if you remember the list of things that we need to know, we talked about how we need to know the rate low, but now you know that the rate low, you know how to find X and Y. So overall order, right? Then here we say integrated. So these are the list of things that we need to know. Integrated rate lows, right? These are the ones that rate lows. These are the equations, right? And then equations and graphs, right? Equations and graphs. And then two methods to determine order, right? So we need to know that. And then we also, by the way, can know the rate constant, right? If we don't know the rate constant of a reaction, we can experimentally calculate it, because let's go back and look at what we're looking at. Look at this, right? If you already gave me the rate law, so the rate law is say the rate is equal to the constant times F2 to the first, ClO2 to the first, right? Guess what? If we pick any line, from my experiments, right? If we pick any line, it will have this concentration, which is this, right? It will have this concentration, which is this. And what will it have? It will have the rate, which is this. What does that tell you? It tells you that you can find the K. From any of the 3 points, you can find the K. The K will be equal to the rate over this one times this. Does that make sense? So after you have the rate low, you can measure the rate constant experimentally. This is an important experiment in chemistry that I want everybody to know about. Let's look at another example. This is another boring example. The boring example because it zoomed in. If you were able to see me, you were able to see. Okay, good. All right. So to see. But this is what I was showing you guys. If you haven't been able to see me, to see everything that I was showing, this is what I've been determining on my slide for this reaction. So you can go back and adjust your notes from that. Okay. All right. So let's look at another example. This example is, it says determine the rate law, then calculate the rate constant for the following reaction, right? So it gave you a reaction, then it's asking you for the initial rate law. It gave you data, right? And then look at this. Rate law is this, but we don't know what X or Y is. X or find X. How do we find X and Y? You look at the reaction, right? You look at, okay, this one stays the same. Oh, this one is half of it, right? But don't be confused, right? Don't be confused. The best way to, you can do this, you can be like, oh, okay, this one halved, right? So you can read it, backwards, right? Because there's no order of reactions. You can be like, oh, okay, this one stayed the same, and then going up, this one was multiplied by 2, and then let's see what happens to the rate. The rate also multiplies by 2, so that means our X is 1, right? Why? Because again, this one stays the same, one multiplied by 2, both of them, right? And then you go to the next one. The next one, you're like, oh, okay, let's see when the second experiment happened, right? This one stays the same. This one stays the same. And what happens to this one? Oh, it also multiplies by 2. Who knew, right? And then you're like, okay, when this multiplies by 2, what happens to the rate? Oh, look at this. This also multiplied by 2. What does that mean? It means that Y is also 1. Now, what happens if we multiply by 4? What if we had 4.4 here? If we had 4.4 here, our Y would have been 2 instead of 1. Does that make sense? I hope it's clicking. Ready? So the rate will be equal to, the rate low will be equal to K times S times I, right? Because this is 1 and this is 1. And then the second question is, constant is K. So K is, you can pick any of the 3 points, and then you're going to take the rate over this times this, right? So it's going to be the rate over this times this. Then you get the beautiful rate constant. Does that make sense? Now, something that's very weird, the rate constant changes. So you have to figure out not changes, but the rate constant units change a lot. So the rate constant unit depends on what you have. So you always have to work out the rate constant units depending on what you have here, what you have here, what you have here, whether or not you have 2 or 3 or something like that. So you always have to work out the rate constant units, right? Does that make sense? I think that makes sense. But if it doesn't, replay, rewind, rework some of these problems, look at the samples provided, try to practice on the homework. Then, if all this fails, reach out to me and I'll be more than happy to explain. All right, so let's look at something else. Let's look at two things before we're done with this video. All right, so the first thing that I want to talk about is called half-life. Half-life, right? I think you've heard of half-life before, right? You've heard of half-life before, and half-life, what is it? Is I have here. Oh, this we don't have to worry about this. No. Oh, there it is. Okay, half-life, right? Is the time it takes for half of the product to go away. Half-life is the time it takes for half of the product to go away. We use half-life in drug discovery in the hospital. We use it in radioactivity, right? So half-life is the time it takes for something, for half of something to go away. Does that make sense? So let's say I was drinking coffee earlier, right? Let's say I drank 100 grams of coffee, right? It takes about 6 hours for half of it to go away. That's the half life of coffee. That makes sense. So let's look at it in an easy way, and then we're going to relate it to our kinetics. So let's say I started with 100 milligrams of coffee, and then after 6 hours I have 50 milligrams. After another 6 hours I have 25 milligrams. Then I have another, after another 6 hours I have 12.5 milligrams, right? So this is one half life, two half lives, three half lives. So I can ask you a question like, hey, after three half lives, how much will I have left? Then you can be like, oh, okay, it's going to be about 12 milligrams. Or I can ask you like, hey, after 18 hours, right? After 18 hours, how many grams will I have left if the half life is 6 hours? And then you can be like, and the half life is t1 half like this, right? You can be like, oh, okay, if the half life is six hours, then for 18 hours it will be three half lives. You can do that. You can do that. Love that formula. I use it all the time, right? So again, if I can give you a better formula, right? So it's like, again, you can set it up correctly like this, but let's relate it to, and this is kind of another way to think about it, right? If you have this much in a reaction, and then after one half life you have half of it, right? After one half life you have half of that amount. After another half life you have half of that amount. After another half life we have half of that amount, right? And then we keep going. That makes sense. So A0, as we already seen, is the initial amount, right? And then after one half life, what do we have? A0 over 2, right? That's the concentration. And then after another half life, A0 over 4. After another half life, A0 over 8. Get me now? So that is that. So when it comes to the first order reaction, I want you to look at this, right? When it comes to the first order reaction, we already know that the equation for the first order reaction right? The equation for the first order reaction is, right, time, right? If you remember, time kt is equal to 1 over a. No. Okay, so 1 over a is equal to 1 over a0 times k plus t, right? Wait, we can actually, I can actually show you how to get it. That way you understand. Because some people actually need to see it laid out. Understand why, right? So 1 over a is equal to 1 over a0, the initial time, plus kt, right? At time that's half-life, right? The concentration that we at is equal to 1 over a0 and a half. That's what we say, right? 1 over a0, one half of 1 over, I mean, I can do it, right? So a at time equals t half or half life, our a is equal to a0 over 2, right? So we're going to substitute a0 over 2, and then it's equal to 1 over a0, 1 over a0 plus k times t half, right? You with me? So then look at this. I'm going to move this on to the other side, and then I'm going to solve these. So this will be equal to, so 1 over a over 2 is equal to 1 over, no, it's going to be, it's going to be equal to 2 over a0, right? And then let me move this here, minus 1 over a0 is equal to kt, right? Then this gives me 2 over a0 minus 1 over a0 is 1 over a0 is equal to kt, and my t is t and a half, right? Which is half-life. So kt and a half, right? And then that tells me that our t and a half is going to be equal to 1 over k, right? So this is where we get our expression of half-life, right? Is it the same? Yes, it is, right? Okay, so this is where we get our expression of half-life, which is, hey, half-life, when you have a first order reaction, the half-life is going to be equal to 1 over k times our initial concentration, right? This is a powerful equation because if I ask you like, hey, what's the half-life if I start with this, you can just use it using the red coin, right? Very, very easy. So we can find the half-life very easily. But look at this. When you have a zero order reaction, right? The zero order reaction, same thing, right? We do the same reaction, but again, oh, this is actually a second order. Second order, the first order is going to be equal to this. The zero order is going to be equal to this, right? So the half-life, right? So I did this for the second order. My mistake, it was not the first order, it was the second order. If I do the same equation for this, right, which is our first order, right, I substitute a to a0 and I substitute t to t and a half, this will be our half-life, right? And I love this half-life, right, because it doesn't involve a0 or a1. So the half-life for a first order reaction, so this is the half-life for a second order reaction, right? Second order reaction, if we had to do the same for a first order reaction, do it very quick to show you, that way you will know where the number came from, so that you're not like, where did this number came from? So if you remember, ln of a is equal to ln of a0 minus kt. That is the expression of the first order reaction, right? But our a at time equals half-life, our A is equal to half or equal to ln of A0 minus KT, right? So let's go ahead and do our calculations. Ln of A0 over 2 is equal to ln of A0 minus ln of 2. That's just the nature of ln, which is equal to ln of A0 minus KT. You might see where this is going because ln of A, you have the ln of A on this side, ln of A on this side, so we're going to just subtract, right? Ln of A0 minus ln of A0 right, minus ln of 2 is equal to minus KT, right? And then ln of A0 minus ln of 0 is 0, right? 0 minus ln of 2 is equal to minus KT, which tells us that KT, so I'm going to remove the negatives. KT is equal to ln of 2, right? Which is 0.69 or something, 93, something like that, right? So this is where this number comes from, guys, right? 693. Wow, I got it. 693. So T, which is our half-life, the T at half-life, right? T at half-life is equal to 0.693 over what? Over K. This is where it comes from, right? So now you know how to express half-life in all of it, right? So go back to our list of things to know. Then I will add half-life. Half-life, right? And this is, you gotta know the meaning, equations, and calculations, right? That's half-life. That's half-life for you, okay? So one other thing that you might have learned, you probably have learned it, right, is that some reactions, instead of having one steps, you have multiple steps, right? So some reactions, instead of, for example, going from NO to N2O2, right? So you take, sometimes you take, these arrows being out of place kind of frustrates me. Let's move them here. Let's move the versions. Mhm. Just give up, guys. Okay, so look, if you take, sometimes you take NO plus O2, you get NO2, but you detect N2O2, like what happened? Well, two reactions happened, right? The first one was NO plus NO is equal to N2O2. Then the second one is N2O2 plus O2 is equal to 2NO2. But because the N2O2 being produced is being used up to give us our final reaction, N2O2 gets cancelled out, right? So the final reaction is still the same, but it takes two steps, right? So these are called elementary steps, right? And or elementary reactions, and we call this a reaction mechanism or a multi-step reaction, right? So we care a lot about this, and again, depending on how many reactions, right, we will look at different steps. So if the one step, if the mechanism uses one molecule, right? If the elementary step uses one molecule that gets used up, we call this a unimolecular reaction. And then if he uses two, bimolecular reaction. If he uses three, termomolecular reaction, and so on and so forth. So it's called the molecularity of a reaction. Care about this a lot. Why do we care about this? Because depending on different reactions, you have different rates. So unimolecular reactions, it has one rate. By a biomolecular reaction, right, it has two molecules, right? So everything that we've been calculating uses A. But if you have A plus B, right, if you have A plus B, you're going to have to adjust the equation. You have a different rate. If you have A plus A, you're going to have a different rate. So we use different mechanisms, right, depending on what the molecularity of the reaction is, right? And the rate determining step is the one that is the slowest. So we need to know, if we have a multi-step reaction, we need to know the slowest reaction. So this is where the kinetics come in. We need to know the slowest of the reactions so that we know how we can measure the rate, right? Because again, if you have two reactions happening, right? You have two reactions happening, and I'll talk about this later. But if you have two reactions happening, then two of one is slow and then the other one is fast. It doesn't matter what the slowest is, right? We have to wait. No, it doesn't matter what how fast the fastest is. We have to wait for um the slowest, right? If you have two people that are getting married and the husband is just uses is driving very fast to the courthouse and the bride is taking their time, doesn't matter, like how fast the marriage is going to happen will depend on how fast the bride gets there. It doesn't matter how fast the groom is. Does that make sense? So if you have two reactions happening, the rate determining step is the slowest one. So we do calculations using the slowest, right? So let's go back to that list of things to know and then add reaction mechanisms, right? Reaction mechanisms, mechanisms, rates, and molecularity, right? Whether or not it's unimolecular, biomolecular, or thermolecular. Very, very important step. Now, something very interesting happens in our body, in nature, because a lot of reactions are very slow. A lot of reactions are very slow in real life, but they end up being very fast. Why? Because we use things that we call catalysis. We use things that we call catalysis. So we use catalysts. So we need to know about catalysts. And catalysts, right? Catalysts are things, are substances that increase the rate of chemical reaction. They are things that increase the rate of a chemical reaction. And how do they increase the rate of a chemical reaction? They reduce the energy required, right? So if I ask you like, hey, how do catalysts reduce, no, how do catalysts increase the speed of the reaction? They do that by reducing what we call the activation energy. So they lower the activation energy, which is the energy required to actually make the reaction happen. And we'll talk more about that. We do that by lowering the reaction energy, right? So and speaking of the reaction energy, let me tell you something about how to calculate it. So the reaction energy, this is the equation, right? It's called the Arrhenius equation, and this is something that I really want you to know about as well. The Arrhenius equation, and this, I don't like the way they do it here. Let me show you the easiest way to do it, right? Writing down the Arrhenius equation is called, so Arrhenius equation tells us that the rate, right? Not the rate, but the rate constant, K, right? We already know about K. The rate constant, K, is equal to A, which is the Arrhenius constant, right? Times E, this is the number on your calculator, right? EA over KT, right? And we can talk about where this formula comes from, but this is called the Arrhenius equation, that, not KT, but RT. We already have K, RT. And again, I want everybody to understand this. This is called Arrhenius equation. This is the last thing that I want you to understand. The Arrhenius equation gives us activation energy, EA, activation energy. And then again, catalysts lower this by catalyzing the reaction, right? Catalysis, right? So again, if I ask you like, hey, what is the activation energy? You will find it because guess what? K is the rate constant. We know how to find it. A is the Arrhenius constant when you will be given to it. E is a constant as well on your calculator. R is a constant as well. So for each equation, for every equation given, you can find the activation energy, right? For every reaction given, you can find the activation energy if you can find T at a certain temperature, right? Just gotta remember that the temperature is in Kelvin. Temperature is in Kelvin. R you'll be given, E you given, A you given. So you can find EA. You can find EA by this, right? Does that make sense? So make sure that you know how to do this. I will give you a formula. Let me actually give that to you right now, because some people might have trouble finding this in this form of equation. So I'm going to give you a different form of equation, right? So we're going to make this linear, right? We're going to make this linear, meaning we're going to make this straight. And this is ln of k. So if we convert this into linear, we're going to say ln of k is equal to negative EA over R RT, right, plus ln of A. So if we move this around, we'll get this, right? So either you memorize this or this. This is much better actually. I would memorize this one because then you can find EA much easier, right? So these two formulas are the same. It's just that one of it is linear and makes it much easier, right? And then another formula, by the way, and I'll show this to you. And you know, this we do in the lab. If I have two rates and two temperatures, I can measure, right? I can easily measure the way this the way they differ, right? I can easily measure the activation energy by saying like, hey, ln of K2 over K1, right? So this is just moving these two reactions. I can say ln of K2 over K1 is equal to EA, which is activation energy, over R, right, times the temperature, which is 1 over the temperature, minus 1 over the temperature, right? This right here is the equation. I don't want you to memorize this one, but this one is what we use when we have two temperatures and two rates, meaning you measured, you did the equation in two rates, and then you can, you have the temperature, you've measured the rate, and then you can measure the activation energy. This is in reality how we measure the activation energy in the lab, right? So that's the last thing that I want you to know how to do, and then let's put that on the list as well. Okay, so I'm gonna put it here, which is activation energy Arrhenius equation and catalysis, right? Catalysis or catalyst. All right, does that make sense? All right, guys, that is all I have to say when it comes to kinetics, right? um, like I said, kinetics sometimes tend to be difficult for some students, but it's because it's a bit harder than your other equation, your other chapters. But it's still understandable if you follow all the steps, if you take time to with it, revise, you practice, and then you ask questions where you don't understand. um, Practice is crucial. Remembering the equations and knowing where the equations come from and then remembering them is crucial. But again, I did my best to give you kind of the things that we need to know, and how to make sense of it, which is we started with what is the rate of the reaction. We saw the rate expression. How do we express the rate? Then we talk about the rate law. Then we talked about the reaction orders, with respect to A and B and how to find them. Then we looked at the overall order, which is, take the two and you add them up. Then we talked about the integrated rate laws, which are those equations and graphs that we need to remember. And those are the graphs and the equations that will help us experimentally to find the reaction order. So, this graph right here is my favorite because it puts almost everything that we discussed together, right? So these are the integrated rate laws, and then these are the graphs to go with them, right? So we know those as well, right? So we need to remember those. And after that list, after that, we talked about the two methods to determine the order experimentally, the order and rate constant, right? We talked about the method of graphing and the method of looking at the rates and see, they double. If you double the concentration, that it double, or does it quadruple? So from there, or does it say the same? And from there, you have a zero order, first order, or second order. Then we talked about the half-life and meaning, and then the equations of half-life. We need to know these in order to calculate this, and even talked about where those equations come from. Make sense of it. Then we talked a little bit about the reaction mechanisms and how they affect the rates. We talked about the molecularity of the reaction, and they ended it with what is the activation energy. And then when we lower the activation energy by catalyst, um, we make the reaction go faster. And then we finish with the Arrhenius equation, which is a very important equation that we can use in order to measure what? Measure the activation energy given the rate constant and temperature, right? So this is kinetics again, very important chapter. Calculation heavy, but you should understand it. Equation heavy, but you should understand. Remember it, and not hesitate to reach out, guys. I'll be happy to get on a call with you, send you an explanation email, find a video that maybe explains it better, or even sending you more practice. But that is all I have for you. If you have, don't take time to practice, and I will